So two kind of big questions we're going to ask here in the first half of class. What is a rate of change function? Could you give a articulate response to what is it? What is a rate of change function? And what is meant by rate of change at a moment, or what may be called instantaneous rate of change? Okay? So what is a rate of change function, and what is rate of change at a moment? Again, if there was one or two or three things, this would certainly be one of the things I would want you to leave the course with, the ability to understand and explain this. All right, so I've got this situation here. A ground fault opens, and scientists begin measuring the width of the opening in centimeters at a certain point along the fault. They take regular measurements for several months, and they model the data with this function W, whose graph is shown below. So we have time since the fault originated in months. That's our input quantity. And then the fault width in centimeters is our output quantity. Okay? So some questions to think about. Is this an accumulation or rate of change function? And what does the point 1.5, 5.225 represent? Go, talk. Okay, accumulation function or rate of change function? Fault width in centimeters. Accumulation or rate of change? Accumulation. It's not a rate of change, it's an accumulation. It's just how wide the fault is in centimeters. So it's an accumulation function. So the point 1.5, 5.225 represents that at 1.5 months since they started measuring, since it cracked open. Is it a rate of change? 5.225? No, it's a width. It's a width in centimeters at that point in time. That's the measurement they took at 1.5 months. Okay? And the graph, what does the graph consist of? No, it's not a curve. I mean, yes, it ends up being a curve. What does the graph consist of?
Every single point.
Every single point like that one we just explained. That emerge as time goes by, right? So time goes by, and for every moment of time that goes by, you get a point, just like the one we explained. And then all those points together make the graph. It's just easier to draw it fast with a continual kind of line or curve rather than trying to dot every point. But you're looking at a whole mess of points, right? You're just looking at tons and tons of points, just like the one you just described. Okay, cool. So now what I want you to do is by observing the graph, describe what the fault width is doing at each x value. As, is the fault width holding constant? Or is the fault width increasing or decreasing, and then how? Slowly, moderately, or quickly? So we'll do first, so here's a whole bunch, we'll do the first one together. So at 0.25 months, what would you say? Is the fault width holding constant or increasing or decreasing? Which?
It's increasing.
Increasing. And would you say slowly, moderately, or quickly?
Quickly.
Increasing, quickly. You do the rest. Go.
Increasing. Moderately. Moderately at 5 and 6, I would say. Rising slowly at 8.
Oh yeah, yeah.
Okay, so your answers might vary a little bit, but if one of your answers is a lot different than what I put up here, then that's of concern. But if you were off by, if you said slowly and I said moderately, or if I said moderately and you said quickly, that's maybe just subject to, answers may vary a little bit. But this is what I would say. At 1, increasing moderately. At 2, holding constant. All right, at 3, decreasing moderately. At 4.1, holding constant again. At 6, increasing moderately, and at 8, increasing slowly. Were your answers like that? Similar?
Yes.
Okay. So does that make sense so far?
Yes.
Okay. So some questions here for you. What does a rate of change value mean in this context with the fault width? How can we estimate individual rate of change values? And estimate, so then we'll do 5 together. But so you're answering 3 and 4. So answer 3 and 4, talk about it. Go.
Increasing quickly.
It's just like
Yeah. Talk to me. Wait, talk to me. Oh, I thought you said professor.
You're our professor, aren't you?
Thought he wanted to ask me a question.
I apologize.
Oh, there's nothing to apologize about. Okay, anyone want to take a stab at number 3? What does a rate of change value mean in this context? What is a rate of change value? Rock, go for it.
How much the width is changing at any moment in time relative to...
Okay, he said how much the width is changing at a moment in time relative to the time. A couple nods down here. That was pretty dang good. What were you going to say?
I was just gonna say relative to time, since just to be accurate, but what he said is right.
Okay, was there a hand in the back? All right, so that's actually what we want to kind of discover here or reinforce. And so how can we say here at 0.25 months, we want to estimate the rate of change at 0.25 months. What is it going to take to do that? What is it going to take to do that? Adam? He wants a change in y over the change in x. Okay, so can I say here's about 0.25. So if could I take like a change of time of say like 1 month and the corresponding change in width? How about that? That'd be good? What's that? All right, so right, exactly. So if we were talking about the rate of change at 0.25, what is required to do that? So yes, we're going to take the change in fault width over the change in time in months, but under what condition? Small change in time. So here's how we can do that. Oh. No, no, no. Okay, so 0.25 months is this line right here. Can you see the lines? Yeah, good. So here's the light blue line. So there's right there is 0.2. That's on the 0.25 months line. All right, so what's happening here is each square horizontally in months is a quarter of a month. But vertically, it's half a centimeter. Okay, so write that down. Each square this way is a quarter of a month. Each square going up and down is a half a centimeter. So I'm going to do this first one with you, and then the rest you'll do on your own. So here's what we're going to do. Make it easy on ourselves. So we'll go, I'll start right about here. Beautiful. All right, so estimate the rate of change. So a quarter of a month is your width of your squares, a half a centimeter is your height of your squares, and estimate the rate of change at 0.25 centimeters. Go. Can you do it? Okay, horizontally, a quarter of a month is each square. Each square vertically is half a centimeter. Does that answer it? Each square is a quarter of a month. So, from here to here is 1/4 month. From here to here is 1/2 centimeter of width.
Yes, that makes sense.
We're just estimating. So make it easy on yourself.
How many lines?
Okay, so what change in time did I show you and help you with here? What change in time is that? Well, half of a quarter of a month. Half of a quarter of a month, like an eighth of a month. And what was the resulting change in width? Like 1 square, right? So half a centimeter. So find that rate of change, or we're estimating the rate of change here. What'd you get? 4 sounds good. Centimeters per month. Okay, so now from here on out, so I helped you with the first one, but you're going to do the rest yourself. I'll zoom in on each one, and you're going to do it. Okay, ready? So here's for 1 month. 1 month. Easy one. Go. This line. What happened? Where'd it go? I'm just not going to touch it. So the left side of the arrow is on the 1 month. The left side, that vertical side of that arrow, That's the 1 month mark, okay? This one's easy. This one's easy.
It's only half or a quarter. And half or a quarter is an eighth.
Change in y is?
Oh, 1. 0.5.
Make it easier on yourself. So the easiest way is just consider like it's at that corner and then it's at this corner. So
So
change in y is
0.5.
half a centimeter. Change in time, quarter of a month. Quarter of a month, half a centimeter. Rate of change estimate?
2.
Did you get 2? Is this making sense? Okay, 2. Ready? Here we go. So I recommend go from there. So you can start behind a little bit. That's fine. Go from there to there. What's the change in x and the change in y? What's the change in x? It's a little easier to see if I'm not that zoomed in. Okay, estimate for rate of change. How much does the fault width change over that quarter? Make it easy on yourself. We're just estimating. How much does the fault width change over that quarter month? 0. Or just a little teeny bit. So we're just estimating, so we're going to call it 0. Okay, here we go. So this is 3 months, right along this line right here. This is 3 months. That again. Change in x. Quarter of a month. Change in y. Negative a quarter of a centimeter. So half of a half. Estimate for the rate of change. What do you think? Negative 1. Is that what you got? Oh, all my things went away. So tell me what we had. 4.
2, 0, negative 1.
Okay. 4.1. 4.1. Estimate. Rate of change. 0. 6. Just 2 more to go. Here's 6. There it is, around 6. Estimate for the rate of change. Everyone's working on this, right? Hey, can you guys make sure everyone's on task? Thank you. Okay, what'd you get for your estimate?
2.
Hearing 2. Agree?
2.
Does everyone know what's going on by now? Can you do this? So okay, so I just want to make sure that you're not totally lost. If you got a question, ask one of these guys or ask me. So we had 0 and 2. One more to go. All right? 8. Which one is it? Okay, go. Let me get a better view, sorry. This is better. Here we go. There we go. Here's what I see as an easy way to do this one. Ready? That's what I see as an easy way to do this one. All right, so it's kind of hard to don't ignore this line right here. Ignore this line right here. You got to ignore that one. That's just showing the y value of the current point. What's the change in time? Half a month and half a centimeter?
A quarter.
Half of a block, right? It's half of a square. Square goes from here all the way up to here. So half a square there would be a quarter centimeter, and a half a month. Estimate for the rate of change. 0.5. 0.5.
Does it matter which one we write it to in fractions or decimals?
Not really.
Okay.
Okay, any questions? Are these the estimates we had? Okay. So we did number 5. We estimate the rate of change at each x value in the table. We're estimating the rate of change. So number 6. What is a rate of change function? What is a rate of change function, and what does the table have to do with it? Go, talk. What is a rate of change function, and what does the table have to do with it? Can you explain what a rate of change function is? Okay, somebody new. Want to take a stab at this? What's a rate of change function? What does the table have to do with it? What do you think? This is what everyone should be able to answer this when you come out of calculus. What is a rate of change function? How would you describe? What is it? Yeah.
It shows how the width of the fault is changing.
Okay, so it shows how the width of the fault is changing at any point in time. It shows how the width of the fault is changing at any point in time. No? What did she say? What did I say? How it's changing. You're saying you're saying specifically how fast. How fast the fault width is changing in relation to the time. But as a function, then, so what does it mean that it's a function? At a certain point? What's the idea of a function? We have exact, approximate functions. Is it just one rate of change? Here's the point. It's every rate of change for every time since whatever your domain is. So starting at 0 in our case, we see up to about 9 months. You get every rate of change like the ones we estimated along the way. So you can choose anytime you want. The function will give you the corresponding rate of change. So what does the table have to do with that? The table is a representation of the function. It's showing it is the rate function for some of the time in months. So our input of the function is time in months, and then the output is the corresponding rate of change. Again, a rate of change function is just a whole set of lots of points. Each point now, for this function, the rate of change function would be a time in months and the corresponding rate of change telling you how fast the width is changing. Okay, so a rate function then gives you every rate of change for every time in months. This table is a representation of that for some of the points in time along the way. How do the values represent what we first did, what the fault width is doing? The second column of the table. So how do the numbers represent these descriptions that we made in the second column? Go. Answer. So you should be discussing that the numbers are telling the exact story that our descriptions did. If it's increasing, then what about the number of the rate of change? Positive. Positive rate means increasing. We have the fault width is increasing. Okay? A large positive number means what about the rate of change? Increasing quickly. Down here at the end. A smaller positive number means it's increasing more slowly. Okay? 1 or 2, we called that a moderate rate of change, right? We called that moderate. So you should see that these numbers are putting a quantity, they're putting a value on exactly what we described in terms of what the fault is doing at those times. Do you see it? Okay, so here is the width function that I'm graphing, the blue function. What does the mastery exam have to do with this discussion? There's the width function. It's graphed as the blue graph, all the points on the blue graph. W of x equals 2 radical 5 sine x equals plus x to the 1.5. What does the mastery exam have to do with this table that we built and our discussion? Go, talk. Okay, let's hear somebody new. What do you think? So now I'm giving you this exact accumulation function, accumulation of width over time as W of x equals 2 radical yada yada. What does the master exam have to do with this? Tell me.
Master exam tends to ability to change that from exact accumulation function to exact rate of change.
Okay, so if we take the derivative, we'll get the exact rate of change function. And then what does that have to do with what we're doing?
We're just proving it.
What's that?
We're just proving it.
We're just-
By we equate the points on that rate of change for the accumulation function.
Okay, so there's. What were we going to say?
Like you can take any point in time and apply it to the rate of change function and find the rate.
Okay, so you're saying you could take your rate of change function, apply it to any point in time, and find your rate. So, like for instance, if we find the rate of change function and plug 2 into it, what do you think will happen?
It's gonna give us exact close to 0.
What is it?
It'll be close to 0.
She thinks it'll be close to 0. Agree? Yeah, so if we get the derivative, which is the exact rate of change function, that allows us to plug in a moment in time and get the exact rate of change. Let's do it. Go. Great practice. For those who do not pass the first attempt, who have not taken the first attempt yet. Great practice.
Well, let's make sure that the code is right.
Yeah. Who's learned something? If you put that like that in web worker graphing calculator, it will count it as wrong. There you go. Let me see. You got 1.5 next to the yeah.
So you want us to do it for only x, but just
What do what you want to do.
I mean, what as well?
What would your intellectual curiosity want to do? What would I love it if you answer? How would I love it if you answered that question? I'm not getting it. Okay, hope everyone can do this. Where do we start? What's the structure? What's the structure? Chain rule. Okay, it's one function. Actually, the structure is constant. The overall structure is actually constant multiple. It's 2 times something. So our rate of change is going to be 2 times the rate of change of this. Now this structure of this is chain rule. So we start with f prime, which is 5 cosine x plus. You should all be able to do this. You're masters, right? Or you should be. Right? Rate of change of the interior. Rate of change of the interior times 1 over 2 rate of change of a square root function. What do I put in here? Exactly what's in there. The rate of change of the exterior with respect to the interior.
We could have gone to the outside in as well, right?
Yep, it's fine. Did you get it right? Did you get it? you could use the product rule and then plus 0 times. Yeah, so that's a lot more to think about. So yeah, you're just applying product rule to that when you don't need to. Okay, so pick a couple of these x values and evaluate the rate of change exactly using the function and see what happens. Okay, just pick a couple. Everyone pick a different couple. So you can pick 1 and 6 or 0.25, 4.1. Pick a couple. Using graphic calculator? Yes. So much easier. Use GC. It would be so much easier to get these using GC than a handheld, right? Okay. Put these to the side for now. Put these to the side for now. One more? Need another one? No. Just put them off to the side. Don't keep your focus on what we're doing. Just put these on the side. Okay, so if you plugged all those values in, you should, so we can check. At 0.25, I got 4.79. Agree? And here's the rest. See if you agree. Okay, so if you had your choice of how to build this table, do you want to do it by zooming in at these 6 places and estimating, or do you want to take the derivative, plug the values in, and generate the numbers? Which is more efficient? The derivative is quicker, and why is it? There's another reason it's better. They're exact values. Okay, they're exact values. So this is kind of the beauty of these derivative rules is you can find rate of change at any time. You get it exactly, and you can get it efficiently. GC, you could just plug in W of x. You could tell GC to find the derivative, and you could tell GC to find all these values, and like that it could do it. So technology could do it super quick. But, okay, listen. That does not, by any means, minimize the time I'm not saying it's not important of what we did. In fact, it was very, very important that we did what we did by zooming in on all those points and estimating the rate of change, because you have to understand that that's what a rate of change is, and that's what these values mean. What do these values mean? They mean the relative size of the change in y to the change in x for a very small change in x. Right? How is y changing for a very small change in x? That's what those values mean. And zooming in and doing those individually is crucial that you have an image of what a rate of change value means. And so I think that helps. But then we see that the mechanics of it, the taking the derivative and cranking out values is very efficient and it's exact. But you got to know what those numbers mean. Okay, so there's no better calculus class than this. You're getting the best. I hope you appreciate that. Do you understand this? This is like the one thing I want you to get out of the semester, if there was one thing. All right, so let's look at this on GC. So there's the function. Okay, so I put the trusted form up there. I put the trusted form, and I made h really small, right? Our trusted form would be f of x plus h minus f of x over h for a small h. So let's give me our estimates first. So at 0.25, what was our estimate? Help me out. 4? What was the next? At what?
At 1, it's
At
2.
1, it's 2, okay.
At 3, it's 0. Oh, no, at 2, it's 0.
2, it's 0.
3, it's -1.
Negative 1.
4.10.
4.10.
6, 2.
6, 2.
8.
That's good. All right, that's good. So I'm plotting points on the rate of change function, right? Our function on the left, which says what? It was increasing quickly, then increasing more slowly, then holding constant, then decreasing moderately, then holding constant, then increasing moderately again. So who knows? So something like this. Okay? So that rate of change function for every time in months is a visual representation of how the fault width is changing as time goes by. So let's graph the trusted form here. So I'm going to graph this our RF function for a small h. There it is. Let's erase the one I drew now. So we see our estimate was very good. Let's erase that one. And then we can check so here's the beauty of graph calculator. Then I put in our mastery derivative, and so we can check to see if we got it right against the trusted form, right? So trusted form is this ratio. Here's based on our algebra, so we can check it. I'll make it purple. It should land right on top of it, and it does. So if I take off, there's the trusted form is gone. Trusted form back. Okay, so here's our side-by-side graphs. We started with exact accumulation. We built the exact rate function by looking at some points, and then we did it by the mastery approach. And we see that is our rate of change function. Gives you the rate of change at any time. The rate of change at any time. Okay, any questions? So next Thursday's quiz is a lot about this, okay? And exam 3. All right, so get out that sheet of paper and then go to
What's the next exam?
a couple weeks, 3 weeks maybe. It's toward the end of April. Was there a question over here? Go to the Blackboard and you want to download if you go to Blackboard, our Blackboard course, go to assignments or reading and homework. I'm about to move it up. Hold on a sec. So at the very top. Okay, it should be up there now. Download that GC file for class in readings and homework. GC file for class. Download that and open that up in GC. And get out the sheet that I just gave you. So our Blackboard, readings and homework, first post, GC file for class, download that, open it up in GC. And when you open it up, you should see something like this. Are we having success? Did you get it? Yes, it's working? Okay, now check this out. With this program, if you go and you put the cursor on the dot, you'll see that like some little crosshairs come up, and then if you drag, you can actually drag that point around. Does it work? So double click, right click, and then you can grab onto it and drag it around. Okay, so I have this expression here, a squared plus b squared minus 2ab. A is the x-coordinate, okay? A stands for the x-coordinate of the point, and B stands for the y-coordinate of the point. So you see that as you drag that point around, you look at the first two command lines, it's giving you the current coordinates, x and y, A and B. And then, then according to the current coordinates A and B, this expression has a value. A squared plus b cubed minus 2ab has a value. Right now, I've got mine at 2.12 and 2.2, and that thing equals that expression equals 5.85 according to the current values of A and B. So what you want to do is this is kind of like a hunt. You're going to move this around, and you're going to find every point where that expression equals 7. So let's see if I can find one here. All right, and between 6.95 and 7.05 is close enough. So, okay, I found one right there. So I found a point. It's at negative 0.266 and 1.81. So on your sheet, you don't have to write the coordinates down. We want to just find as many points as we can and just plot them. So on your sheet, everyone plot this point. You don't write down the coordinates. Just plot the point as close as you can get it, okay? So there is a point such that that expression is within our tolerance of 7, from points 6.95 to 7.05. Okay, and once you plot that, now try to find another one. And you're trying to find every point. Every point such that that expression will be very close to 7. Don't write down coordinates, just get as many points as you can, as quickly as you can. Is the task clear? Don't write down coordinates. Just as many points as you can plot, as many dots as you can get in the right place on your graph as quickly as possible. Yeah? Anybody need help with GC? Is it working? There are points in all 4 quadrants. All 4 quadrants have points that you're going to find. All 4 quadrants. Read on what I'm saying. So, are you able to drag the dot? You're able to drag it around? You can grab it. Right? Now, zoom over here. Now, try to find out. So, it's too small. So, the one direction work is bigger. Go the other direction. there. Pretty close. Good, that's fine. That's good, right there, stop. Perfect. Okay. So that's another one. So on your, so just look at the coordinates. So now you're gonna plot the point on there. I'll do a few too. You can steal mine. All right, you can steal mine.
Yeah, we did.
Your goal is to find every point, and there's some in every quadrant. All quadrants have them. Okay, you can steal mine. You can steal my points. You don't have any of these yet. Anybody get them all yet? What's that? Is there an infinite? He's saying there's an infinite number. Anyone get them all yet? There is or there isn't? There isn't. There isn't an infinite number. So did you get them all? You got them all? Okay. So you got them all. Did anyone else get them all? What are we really saying? We're really saying we want what? We want x squared plus b cubed minus 2xy. And what do we want that to be? Equal to 7. So if I graph this, what's going to happen? So I want to graph, oops, y. What if I graph that equation? What's that going to give me? You're telling graphing calculator, show me every place in the plane that meets that condition. That's what you were doing. So let's see what happens. Did you find all the points? No. There is an infinite number of points. Again, so a curve is what? It's points. Okay, but this is a little bit different than a function, right? Because what we're saying is we want every point x and y that satisfies this equation such that that expression is 7. Well, it just showed you all the points that satisfy that equation. So if I pick a point out here, tell me about this point right here. What's true about the coordinates of that point?
It's not equal to 7. Oh, according to
The coordinates of that point. What's true about the coordinates of that point? Relative to this equation.
It's not.
So negative 4, 2. What can you say about negative 4, 2 relative to this equation? It's not equal. That's. Go ahead. What are you going to say? Okay, not what's not equal. It's not equal. What do you mean? So negative 4 is not equal to 2. Is that what you're saying? That's right. If you were to plug negative 4 and 2 into that equation, you would not get 7. All right, what about this point? Right there. Yes. You would get 7. You plug on the blue one, take those coordinates x and y, you plug them into that, it would satisfy that equation. You would get 7, and it would satisfy that equation. So that's what a graph is. A graph is all points that make the equation true. Whose coordinates make the equation true? Okay. No. Have a good weekend. Look on Blackboard for all your tasks.